Hey everyone, Dr. Jake Order here, and in my previous videos I talked about how we can't know anything. Two main reasons. One, our senses could be lying to us, so the world could be in our imagination. It could be a demon that lies through our senses to make our brains think the world exists, but it doesn't really. And really that's just, we could be living in the Matrix. And this was Rene Descartes and Cartesian skepticism. Now the other theory is, even if we assume the world is real, we cannot assume that any rule is constant, right? And so this is called the induction fallacy. And it's the idea that previous events cannot predict with 100% certainty future events. So I could drop an apple 1,000,000 times, but I can't say gravity is real because gravity might disappear tomorrow, and I let go of the apple and the apple flies off into space, right? So that's the induction fallacy. Now the big question there is, should we spiral into nihilism? Everything is meaningless and unknowable, and should we just give up? That's why I've got Nietzsche and Buddha here. These are two actual people who described nihilisms in one way or the other, which is the idea, there is no objective meaning to it all. There is no objective truth. And so, but they both still thought we should make the world a better place, which is interesting, right? So we shouldn't spiral into nihilism because everything is meaningless. We still need to try and make humankind better. And so we can't give up on knowledge. We can't get overly nihilistic about this, the concept of scientific knowledge. So then how did we make science work? We obviously did, even though the induction fallacy is 100% true. We somehow made science work because we've got amazing vaccines, we've got cameras, we've got cell phones, we've got antibiotics. So we made science work. How did we make science work under this constant threat of the induction fallacy and Cartesian skepticism? Well, the first thing that we had to get over was, does reality exist? And my favorite philosopher to tackle this topic was George Moore. George Moore wrote this paper, and he's just like, you want proof that reality exists? Here we go. My right hand exists, and I can prove it because, look, here is my right hand. And my left hand exists because here is my left hand. And it was a bit of a tongue-in-cheek paper to say, reality exists because it obviously exists. The world obviously exists. My hands obviously exist. Can we move on? We're not being productive by discussing that we might all be brains in vats, or, according to Elon Musk, we might all be living in a simulation. It's kind of not a productive position to focus on your life. Let's assume that, yeah, my hands are here, my face is here, the world exists. Can we move on and discuss how do we make the world better? So I love George Moore for this. It was a great little paper. And so the biggest guy, the absolute forefather of modern scientific epistemology, how do we know things, was this guy called Karl Popper. He's a fantastic epistemologist. He also wrote great stuff about why democracies fail, why societies fall to bits. He wrote about ethics. He wrote about lots of stuff. But his work on epistemology essentially became the foundation of science. It became how we do science and how we talk about science and how we discuss science and knowledge. He was a Jewish philosopher who fled Europe during the rise of the Nazis. He went to New Zealand. I really sympathize with that. Go to New Zealand or Tasmania if the world is ever in trouble. They're the safest and best places in the world. So yeah, Karl Popper went to New Zealand, and there he wrote some of the greatest works to describe how we can pursue knowledge under the threat of the induction fallacy and Cartesian skepticism. So he said we still need to pursue knowledge to advance humankind. And sure, we can't know anything, but we can have theories. We can't know anything, but we can have theories about reality. And this is why scientists don't use the word prove, right? We never prove stuff in science. We just say with a high level of confidence, this is likely, this is probable, and this is why it's still called the evolution, or the theory of evolution, even though there's more evidence for the theory of evolution than there is for the existence of Australia, because more scientists have verified evolution than the existence of Australia. We like to the highest level of degree, we would say that we know the theory of evolution is real, but we don't call it a fact. We don't say it's evolution. We don't say we've proven evolution, because we can only have theories in science. We can only have theories, right? And this is what Karl Popper talked about. And that's because, you know, the induction fallacy, for example, perhaps all the evidence that we've accrued for evolution might evaporate tomorrow. It turned out aliens were playing tricks on us and planted all those fossils just to trick us, and all the genetic evidence and every bit of evidence that we've ever collected for evolution was just a trick by a supreme alien species, perhaps. So, you know, we can't know for 100% sure, so we don't say proved and we don't say facts in science. We say theories. So, Karl Popper said, yep, we've only got theories in science, but one theory can be better than another. And we need a framework to describe how is one theory better than another, right? And this is roughly the framework he came up with. And it relies on two main things: predictions and falsifiability. Now, these two things are massively integral, right? So theories should make predictions about the world, and that makes them falsifiable, because if you make a prediction and it doesn't come true, you have falsified your theory, right? So let's break that down a bit more. So if a theory makes a prediction, it is falsifiable. And Karl Popper said if a theory doesn't make a prediction, it's not even worth talking about, right? Because it doesn't describe our reality. It is not useful. It has no predictive utility. So it's not even worth discussing. We shouldn't even put it on the table if a theory doesn't make a prediction, because we can't test it, so we can never disprove it. So it's not even worth talking about, right? So a theory has to make a prediction, and by making a prediction, it is falsifiable. And this big Karl Popper foundation of scientific knowledge. So predictions should also be useful. If they're not useful predictions, it's also not worth talking about. So predictions should be useful, and they should tell us about how the world should behave. Now you might go, you know, some theories, surely it doesn't matter how useful the prediction is. Well, one example is, say I said that there is a teapot that is orbiting the Earth, right? It's a very specific prediction. It is, some might say it is falsifiable, but it is not useful, right? It's not useful to wonder about whether there's a teapot up there. And it's very difficult. It would require all of humans' resources to falsify it, right? Because we would need to scan the entire orbital space of Earth and show that at every location that we ever looked forever, and we managed to look at every single spot, there was no teapot, right? So it's not a useful prediction, so it's not worth talking about. So they need to make theories need to be theories need to make predictions. They need to be specific and therefore falsifiable, and the predictions should be useful and tell us about how the world should behave. And the more specific the prediction, the more useful the theory might become. So the key to a good theory is that it will provide specific predictions about reality. So just one off-the-cuff example of a theory. There's theories of electromagnetic wave theory, and it's incredibly specific about the wavelengths, the antennas, what they should do once they meet an antenna in terms of generating electrical currents that we can now use to transport information. It's incredibly specific predictions by electromagnetic wave theory that are incredibly useful and allows us to create things like the cell phone network of the world. And these useful, very specific predictions allowed us to make the peak technological advancement of mankind, which is the Nokia 2280, which is an invincible phone that had Snake 2 on it, which is peak humanity in my mind. He also said that theories are under this constant selective pressure of falsification. So they make predictions, they make useful predictions, and therefore by making a prediction, they're falsifiable, right? So they're under the constant selection pressure of falsifiable. And he said in this way, human knowledge evolves, right? And the bad theories are like slow cheaters. They die off, and so they don't contribute to our knowledge anymore. So in a way, they don't create progeny. They don't create other theories that build off that theory, because that theory made a specific prediction, which was falsified, so it died off and it doesn't contribute to human knowledge anymore. Whereas another theory might make a specific prediction, which keeps coming true over and over again. The predictions are accurate and thus useful, and so then other theories might build off that. And that's like having progeny and evolving, and your theories building and building and building to make human knowledge even better and more fitter, and making us better at making predictions, right? So he described that it's under constant selective pressure of falsification. And under this, it's not a bad thing if science makes a whole bunch of theories around the same phenomenon, and then some of them will die off as they get falsified, right? And so science is actually, if you read the literature, is full of incorrect theories that later get falsified. And Popper said this isn't a bad thing, right? We need to have mutations. We need to have lots of different theories that are all different, lots of different species, and some of that variation will die off, right? So science will make incorrect theories, and that's an important point. It's not a pure thing. It's like evolution. It creates some fitter theories that make good, strong predictions, and it makes other theories that are worse. They make these predictions that are falsified, and so those theories die off. So it's a messy process, human knowledge, is what Karl Popper is describing. A whole bunch of theories that are all different, and maybe some of them aren't good, and they will eventually be falsified and die off. And the good theories will persist and survive falsification over and over and over and over again, making them stronger and better and good at surviving in the future, right? So science is messy. It's full of theories that are all making predictions, and some of them will die off, and the good ones will survive and continue on, like evolution. It's amazing. So let's just look at one example, and physics is always a really easy example for this. Newton came up with Newtonian physics, which made incredibly specific predictions, which were incredibly useful. We built sky towers, we went to the moon and back using Newtonian physics, right? And one of its specific predictions that it makes, and one of its key foundational ideas essential to Newtonian physics, is that 1 second is always 1 second. That second never changes. 1 second stays exactly the same no matter where you are. Einstein came along and said, no, seconds can stretch and shrink depending on how close you are to a heavy gravity object, and that's because it warps space-time, which isn't just space, it's time. So it changes the length of a second, but also how fast you're going. How fast you're going, he showed, changes your experience of a second relative to someone who is not going fast. This is why it's called the theory of relativity, because everything is relative to different perspectives, right? And special theory of relativity and general theory of relativity. These are two things that describe how time can change depending on whether you're near a heavy object or going very fast, right? Now, both these theories make incredibly specific predictions and are incredibly useful, right? So they are good theories. The problem is one of these theories got falsified. So Newtonian physics essentially got falsified because it made very specific predictions about reality. Those predictions did not come true. And one example of this is the global positioning system, GPS, right? GPS is a bunch of satellites in space. Now, all the satellites have on them essentially is a very accurate atomic clock, and they just send the time to your GPS device based on that. Now, it requires incredibly accurate time clocks for the GPS system to work, and using the relative times from the time the signal took to get from each satellite to your device, it tells you where you are in this three-dimensional space of the globe. So when they sent these satellites up with atomic clocks on them, they originally said, let's just use Newtonian physics, let's not worry about special relativity or general relativity, because the changes are going to be so minor, it's probably not negligible. Let's ignore it. What happened was, within one day, the GPS system was out by 10 kilometers. So your GPS would tell you you're 10 kilometers away from where you are, actually. And this is because the clocks on the satellites, their seconds were running at a different speed to the clocks down on Earth. That's because they were moving really quickly, but also because, more importantly, they were further away from the gravity well that is Earth, right? So Earth has a very heavy gravity well, and because we're closer to Earth, our clocks are running slower than the clocks up on the satellites that were further away from the gravity well of Earth, right? And so by making their clocks run out of time with our clocks, we very quickly became out of our calculations to figure out where we were relative to those clocks up in space. Very quickly became wrong, right? So a very specific predictions that were incredibly useful by Newtonian physics set it up to be falsified. That's why it was a good theory. Newtonian physics was a fantastic theory because it was specific and it was incredibly useful. And so by making those predictions, it was incredibly useful, and it was also very falsifiable, and it did eventually get falsified. And so now we have to use Einsteinian physics. And so here we can almost see, right, like Newtonian physics lasted for like 150 years, a very long time, because it was so fit, because it made specific predictions that all came true. It was never falsified for a very long time. So it's such a fit theory that it survived and survived and survived. But then Einsteinian physics outcompeted it. It wasn't, Newtonian physics got falsified and essentially dies off in the evolution of human knowledge, and Einsteinian physics becomes that successful theory that continues on today. Now, Einsteinian physics might be falsified. Quantum physics is doing some weird stuff, which might suggest Einsteinian physics isn't working down on that scale. So, you know, maybe Einstein physics will be falsified in the future, right? And a new theory will come that will describe all of the phenomena from Newtonian physics, Einstein physics, and the new physics coming out. A new theory might encompass it all, right? So that's the evolution of theories and ideas. So now let's look at biological examples. You know, we're biologists for the most part. The people watching these videos, I'm a biologist. How do these principles of falsifiability and predictive utility apply in biology? So let's say we've got this theory. A new drug lowers the number of viruses in your nasal mucus, right? So let's say we take a swab and we want to count how many coronaviruses are in that nasal swab. And what we hope is this new drug will lower the viral load, the number of millions of viruses that are circulating in our nose, right? Now, where did this theory came from? Well, it often comes from sort of biological research. We figured out that this drug, maybe it binds to and kills the virus or something like that. That would lead us to make this prediction about reality, right? So we develop a drug that attacks and kills the virus. So perhaps we would make this theory about what this drug would do in the human population. And let's say we get these results. This is the mean of the placebo group, and this is the mean of the drug group. And so it looks like our theory has made a successful prediction, right? We predicted that the viral load would be lower in the drug group, and it appears to be true, right? So it seems to have survived falsification and has made a prediction, and that prediction has been accurate, right? So this seems like a very fit and good theory, and it will survive the selection pressure of falsification. But what if the data that led to that mean, remember these are just means, was this? So first of all, it's a very small clinical trial with n equals 5. So n is how many in each group, the numbers in each group. So n equals 5 here and 5 over there. And there's a lot of overlap in that data. Now you can intuitively see that the difference in this means could be due to chance, right? It could be due to random chance. So now, has the prediction been accurate, or have we falsified the data? And it becomes a very tough question, right? It's much harder than physics, right? You know, in that Einsteinian satellite example, the satellites were out by 36 millionth of a second after 24 hours, right? Tiny, 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 tiny amounts. But physical phenomena tend to be more consistent than biological phenomena. And so what if we then run the experiment again and we get this result, right? And you could kind of imagine, you know, it'd be pretty easy to get this result after the previous result because the data looks so variable, right? Any difference could have been due to chance, right? So this new drug, have we now falsified the theory, or have we not falsified the theory, right? Was this prediction accurate, or was this prediction inaccurate? You can see that it's much harder in biological sciences than physical sciences. So physics versus biology. Biology is vastly more variable than typical physical events, right? So all the satellites in space were out by 36 millionth of a second after one day. That would never happen in biology, right? When we walk down the street, you could see humans are different heights, right? All sorts of different heights. We're going to be different blood pressures. We're going to have different responses to viruses. We are very variable things by our very nature. So biology is vastly more variable than typical physical events. So the concepts of predictive utility become about confidence. How confident are we that that prediction was real? And how confident are we that we have falsified our theory, right? Now, as soon as you start talking about confidence and chance and probability, you're going to talk about statistics. So this is where statistics enters the chat. And this guy, Ronald Fisher, who's the father of statistics, everything you're about to hear can be, you could draw a point back to this one guy here who was like the grandfather of statistics, right? Ronald Fisher. Yeah, so this is where statistics enters the chat. When the systems are naturally variable, if you want to say a prediction was accurate or that we've falsified our theory, you need to start talking about probabilities, right? Because we've got variable data, right? So we need to say it's highly probable that we've falsified our theory, or we have accurately predicted a response to within a margin, right? So this is where statistics comes in. So with variable data, how do we know if we have falsified our theory or predicted correctly? And the answer is statistics, right? And so rightly or wrongly, when it comes to biological sciences for the most part, but ecological sciences, you know, all sorts of any science about a variable system, a very variable system, rightly or wrongly, statistics has become the foundation of everything that we know, right? So it's our answer to the induction fallacy is essentially falsifiability, predictive utility, and the statistics that underlies those two principles, right? So statistics has become the foundation of scientific knowledge as we know it. So although, you know, statistics can be seen as quite a dry, boring topic, we cannot understand science, we cannot understand medicine, we cannot understand biology without statistics, right? So it is a reality, it is a foundation stone of those principles. And one of those is the p-value. So whether statistics should be used as an epistemological tool, I think is beyond doubt. We should definitely be using statistics as an epistemological tool to understand whether we have falsified a theory or predicted approximately correctly within a margin of confidence, right? We need statistics for that. Whether we need a p-value is an interesting question, but rightly or wrongly, the p-value has become the simple principle of statistics, right? Now, you'll scarcely pick up a paper that doesn't have a p-value in it. Every research paper, every clinical trial, virtually every scientific paper you will ever pick up has a p-value in it. And some people think it's a vast oversimplification of statistics and it's not useful, and there's a good argument for it. But if you're going to go out in the world and understand research, you need to understand a p-value. So in the next few videos, we're all going to go into what a p-value is. Now, I'll give you the strict definition of a p-value, and then I'll try to give you a heuristic of a p-value. Now, a heuristic is sort of a simplified mental model that's a little bit inaccurate, but it's worth it to get that simplicity and that intuition of how it works. So the strict definition of a p-value is the probability, that's where the p comes from, the probability of getting a test statistic as extreme or more extreme as the one you got given the null hypothesis is true. Now, isn't that a mouthful of jargon and almost completely not useful, given how difficult it is to understand every step of that definition? So first of all, I mentioned this word test statistic. What is a test statistic? A test statistic is a way of turning all your data into a single number, right? It's a summary number, right? So it's a way of turning all your data into a single number, and then is that number more extreme, as extreme? What is the probability of getting that one number more extreme or as extreme or more extreme given the null hypothesis is true. So what's the null hypothesis? Well, the null hypothesis is not a simple definition either, but so I think it's much better to give you a heuristic for what the null hypothesis is, right? So the null hypothesis is that there is no effects going on. So this is just a heuristic, by the way, but the null hypothesis is that there is no effects going on. Essentially, your statistical model is kind of useless, and that we should imagine not applying any statistical model to it. But another way to think about it is, it's as if you sampled the data. So say we've got two groups. It's as if those groups were sampled from the same population. That's the null hypothesis, that your data was all sampled from the same population. I'll give you an example, right? So let's say I come up with the theory that people who wear red shirts are taller than people who wear blue shirts. And so I go out onto the streets and I sample 5 people with a red shirt, 5 people with a blue shirt, and I measure their heights, right? The null hypothesis is that shirts have no effect on your height. So essentially, when I took those samples of 5 people with red shirts, 5 people with blue shirts, I was essentially sampling from the same population. I could have just sampled people at random, is essentially what it's saying. I'm sampling from the same distribution of height pools, so I will get approximately the same means in those two groups. That's the null hypothesis, because they come from the same distribution. Now, we reject the null hypothesis if the probability that our test statistic was as extreme or more extreme, given the null hypothesis is true, if that probability goes below 0.05, typically. So if the p-value goes below 0.05, we typically reject the null hypothesis, and so that provides evidence for our theory, right? So if the height of the red shirt people was taller than the height of the blue shirt people, we would then reject the null hypothesis that they are sampled from the same distribution. And so now that we would say they're from separate distributions. Blue shirt people are different to red shirt people, and so they have different heights, right? So that's rejecting the null hypothesis. So let's look at this example here. So a new drug lowers the number of viruses in your nasal mucosa. That's our theory. And we've gone out and we have essentially sampled people with the placebo and people with the drug, and we've got 5 in each group. Now, the null hypothesis is that our drug does nothing. So essentially we've sampled from the same distribution. Because our drug doesn't do anything, it's like we're taking the sample from the same distribution. So we're just looking at the same population, the same variation in mean and viral samples. Now, the p-value of this, I can already tell you, would be over 0.05 just by eyeballing it. They call that the bloody obvious test. And so once we apply the statistical test called the bloody obvious test, we can see that this is not going to be statistically significant. And so we wouldn't reject the null hypothesis. We would accept the null hypothesis that these are from the same distribution. And so we would conclude our drug likely does nothing. So here's a good way to think about the p-value, because there were so many moving parts there. A test statistic, wait, what the heck is a test statistic? How do we turn all our data into one number? That seems weird. And null hypothesis, they're kind of sort of hard to interpret. Let's apply a heuristic for what a p-value is by looking at flipping a coin, right? Flipping a coin. So here's what we're going to talk about. So my hypothesis is my coin is a trick coin and has heads on both sides. That's my hypothesis. There is a heads on both sides of my coin. So the null hypothesis is, we reject the hypothesis, where the null hypothesis is the opposite of our theory there. So my coin is a trick coin with heads on both sides. So the null hypothesis is that it's a normal coin, right? It's got a heads and a tails on both sides, right? So let's say the only way I can explore this concept is by flipping my coin, catching it, landing it, and look at what it lands on, right? So I flip it, I catch it, I land it, and I look at what's on that coin, right? So the question here to get a p-value, this is the heuristic for understanding a p-value, is how many heads in a row would convince you of my hypothesis, and make you reject the null hypothesis. So how many heads in a row would it take for you to accept that this is a trick coin? And let's say we wanted to get to a probability, given the null hypothesis is true, of a p-value of less than 0.05. So I flip the coin and it lands on heads. Do you think it's a trick coin, or do you think it's a regular coin? You kind of got to say, well, I don't know, right? The probability of that occurring is 50%, 50-50. It could have landed on heads just by chance 50% of the time. So then I flip it again and it lands on heads again. What is the probability of getting 2 heads in a row? Well, that's 50% times 50%, which is 25%. So we're now at a p-value of 0.25. The probability of getting 2 heads in a row, given the null hypothesis is true, and the null hypothesis is that it's a regular coin, is 0.25. So then I flip the coin again and I get heads again, and I'm up to 3 heads in a row. Do you now reject the null hypothesis? Well, the answer is no, because now we're up to 50% times 50% times 50%. Half a half a half, which is 12.5%, or a p-value of 0.125. So I still wouldn't reject the null hypothesis, because 3 heads in a row could occur by chance. We can't reject the null hypothesis. So I flip the coin again, and I still haven't broken the threshold, because half a half a half a half, 4 heads in a row, the probability of that occurring is around 6.25%, or a p-value of 0.0625. Right? So I still haven't broken that threshold of p-value less than 0.05, so I still cannot reject the null hypothesis. So even after flipping the coin 4 times and getting 4 heads in a row, I still don't reject the null hypothesis. But now when I flip it 5 times and I get 5 heads in a row, we are ready to reject the null hypothesis. We're at a probability of about 3%, or 0.03, which is less than 0.05. So after getting 5 heads in a row, as a scientist, we would reject the null hypothesis, and the null hypothesis is that it's a regular coin. And we would say that all we can say is we're rejecting the null hypothesis, and that provides evidence for our hypothesis. My coin is a trick coin with the heads on both sides. So we do not accept my hypothesis, right? Because that would be saying we've proven it. All we can say is it provides evidence for our hypothesis. So so we can reject the null hypothesis that it's a fair coin, but there are other hypotheses that this data could be pointing towards. And one of those is it could be a bias coin. Maybe it's weighted so that it will land on heads 80% of the time, right? But it's not a double-sided coin. So rejecting the null hypothesis doesn't mean accepting your hypothesis. It just means it provides evidence for your hypothesis, but there could actually be alternative hypotheses that also explain the data. And so all you can do is reject the null hypothesis. So we reject the idea that it's a regular coin on heads and tails. It's a regular coin, an evenly weighted coin with heads and tails on it. And we say that that provides evidence for it being a trick coin with heads on both sides. But we might even acknowledge that perhaps it just means that the heads is weighted, so it's more likely to be true. More likely to land on heads, rather than saying it's a heads on both sides. So that's a key point there. All we can do is reject the null hypothesis. But here's a really important point. All of statistics has assumptions to it, right? Everything that we do in stats has assumptions, right? And later on, we're going to cover how you need to check that the assumptions that you make are valid assumptions, right? In order to get that p-value. So in this example, we made an assumption that coins do land on heads and tails 50% of the time. I don't actually know if that's true. Perhaps coins, just because of the aerodynamics, perhaps because of the weight of the head, perhaps different coins land at different percentages of times. Maybe it's 50.5% of the time it lands on heads just because of the aerodynamics of the coin. I don't know, but we just made the assumption that coins land 50% of the time. All on heads, all our calculations fall to bits, and the p-value becomes not valid if my assumptions are invalid. If that assumption that heads and tails isn't 50% of the time is invalid. And that's true for all statistical tests. Now, what kind of assumptions do we make in statistical tests? I'm going to go into this much more later, but one of the biggest ones is that the data is normally distributed. We normally make that assumption. And normally distributed is one of those things called a bell curve. Now, I'm going to go all into that later, but I just wanted to set up that, we always have these assumptions when we do our statistics. And if those assumptions aren't true, then our conclusions aren't true. And therefore, our theory, whether we've provided evidence for or against our theory, was completely invalid if we've broken those assumptions, right? So, we've gone from brains and vats all the way through to flipping coins to figure out whether our coin is a trick coin or not. But hopefully this has given you a little insight into how statistics became the foundation stone on which all of our knowledge is dependent, basically, and a little heuristics about some of those, how do p-values work, what is a p-value, and what is a null hypothesis. Now, in the upcoming videos, we're going to go into that. We're going to explore that a little bit more in detail. How do statistics actually work on the ground level? Awesome, guys. Thanks.